Okay, so I will I will start from where I left yesterday. So let me again just put down what I will cover today. So I will complete talking about rates of GW events. And I'm going to put here in brackets threshold dependent. I'll make it clear what I mean by that. Okay. All right. I'll then talk about fitting a hyperposterior to a collection of GW events. So this hyperposterior is what contains information about the distribution of the parameters of the source. So this is what you infer from your hyperposterior. How are the masses distributed? How are the spins of the GW events distributed, and so on and so forth. Okay. I will then come back to the rate of GW events and try to derive a more involved rate posterior, and this time it will be threshold independent. Okay. And this is essentially the rate that was used, or the rate method that was used for the estimation of binary black hole rates at the end of the second observation run of the LIGO-Virgo collaboration. Okay. And finally, if time permits, I will talk about P astro, which is a measure of how significant an event is, and this measure uses the rates posterior. And I will also talk about some properties of the rates posterior. All of this, of course, time permitting. All right, so let me first start by checking with you all. Were there any questions from yesterday? Or everything is more or less okay? All right, so I'm going to take silence as a no, that there are no questions. So let me continue on then with where we left yesterday, where essentially what we were trying to do is to evaluate the rates posterior. This is PR given that you have n events. Okay? So this is your rates posterior. Where we got to was the construction of this posterior on the Poisson mean lambda. And for the particular case where you had exactly 0 events, which is what I mentioned, that at the end of the first observing run, there were exactly 0 events that were detected. So in the case of exactly 0 events, so n equals 0, we had the posterior on this to be exponential minus lambda, right? Then what I pointed out was that the rate is defined as the Poisson mean divided by the population averaged space-time volume sensitivity, right? So then we tried to determine how would you evaluate this population average space-time volume sensitivity. So the way you do this is by evaluating a double integral. Let me just write down the formula because we derived it yesterday. It's T to 1 over 1 plus Z dVc by dZ into P of theta f of Z theta dZ and d theta. Okay. The key point to note here is this function f, which is known as a selection function. What the selection function is essentially a fraction that depends on where the source is located and what are the intrinsic parameters of the source. So what this selection function tells you is that given a redshift or given some luminosity distance, say I have a distribution of masses, what fraction of that distribution will be detected, meaning what fraction will cross the threshold, okay? So that's essentially what your selection function tells you. And the population average part comes from this P of theta. So you need to assume that you know what is the distribution of masses at a given redshift, and then you average it out with respect to that population distribution, and that's where the integral comes in with respect to d theta. Okay? Yes? I'll come to that, how you would infer it. Okay, but for now, let us suppose that you knew what the distribution was. Okay. All right. So this is your population average space-time volume sensitivity. And then now we need to complete the step to go from P lambda given n to PR given n. So that you can derive by just using a Jacobian. So right? Well, what is d lambda by dr? So just look at this here. If you took Vt to the other side, d lambda by dr is just Vt, right? So then PR given n just becomes Vt into exponential all right, and that is your rate given n, where n here is 0, okay, given that you have not seen any event. So this is exactly what was performed at the end of the first observing run for binary neutron star and neutron star black hole events. And what you get is this. So you see PR given S, the S here you can think of as your number of events, which is exactly 0. And you had two different curves, actually multiple different curves, but they are kind of overlapping each other. So let us just look at the blue line over here, okay, the dark blue. First of all, notice that this has the typical exponential fall off as you expect, right? Now, like you asked, we need to assume a certain population, right? So that is what was done to estimate the space-time volume sensitivity. And what was assumed is that the distribution of neutron star masses follows the distribution of galactic neutron stars that have been observed from electromagnetic observation. So that was what was assumed when evaluating the space-time volume sensitivity. You need your P of theta there, right? Additionally, you need to assume some distribution of spins. So what was assumed is that the spins are uniformly distributed between 0 and 0.05 in magnitude. So the spin parameter is your Kerr parameter basically, okay? So it was assumed to be uniformly distributed between 0 and 0.5 because from observation, neutron stars are not expected to be very rapidly spinning like black holes, okay? Now, this thing was repeated for different choices on what your population distribution is to estimate the space-time volume sensitivity. Also, they use different priors. So like I had mentioned yesterday, this posterior on lambda assumed a uniform prior. Now, another popular choice of prior is known as the Jeffreys prior. So P of lambda is proportional to 1 over square root of lambda. This is known as a Jeffreys prior. So that was also used. And that changes the curve quite a bit. And this is again a sort of telltale sign that there isn't much information in your data. You remember what I said yesterday, that if your posterior changes appreciably as a function of the prior, that's usually an indication that there isn't much there in the data. And indeed there isn't much, because you haven't really seen any binary neutron star event, right, at the end of the first observing run. Okay? And upper limits were placed on what is the rate. Do you people have an idea of how you calculate a confidence interval? Okay, so I see some people do not know how one calculates a confidence interval. It's an important concept. So it's also not very complicated, it turns out. So suppose you have this posterior on the rate, okay? And you want to ask the question, what is the 90% upper limit on this rate? So the way you do this is you say that I know that this is properly normalized, then the area under this curve must equal 1, right? So 90% upper limit is defined such that at that value, the area under the curve is 90% of the total area. So 0.9. So essentially then, the equation that you need to solve is integral 0 to R max dr. Find R max such that this is equal to 90%. You have to solve this equation. Okay? That's it. So this is your 90% upper limit. For those who are familiar with statistics, this is the 90% quantile. Okay? Any questions on this? So this is how the upper limit is found. Now, if supposing your rate posterior had a mode, meaning it peaks and then falls. So say you had something like this, all right? So what is then typically done is to quote a confidence interval, a 90% confidence interval. So the way you do this is again not too complicated. So what you say is that the way I calculate a 90% confidence interval is to first calculate a 95% quantile and a 5% quantile, and the interval is basically the edges of that interval. So first you calculate what is your R max, and then you calculate what is R min, and you want to ensure that the area under this curve is 90%. So you can come up with a confidence interval such that you ensure that this area is 5% and you ensure that that area is 5% as well, right? So the 90% confidence interval would be integral Okay, so you solve for R max and R min, and that will give you the edges of your 95% confidence interval. Okay. Here, because this did not have any mode, it didn't peak and fall off, the standard is to just put an upper limit. Okay. Now in general, if say you had n detections, not 0, say you had n detections, and supposing you had some prior which went as lambda to the minus alpha, so some power of lambda, okay. So say your prior okay, and say you had n detections, okay, where n can be any number, any discrete number which is positive, okay. All right. So then what you can show is that in general, following the same process that we did yesterday, p lambda given n after normalization becomes where this uppercase gamma is your usual Euler gamma function, okay, and the rate posterior is simply alright. So this is essentially your rate posterior given n events. And then if you put n equals 0, you will see that you will recover the n equal to 0 result that I derived. Okay? So if you like, for fun, you could try to derive this following the same process yesterday. Just don't set n equals 0. Just keep n as a variable and you will get this answer. Okay? All right. So that completes the first part here. Now I just want to stress what I mean by this is a threshold dependent rate. So essentially in this entire rate derivation, what we are saying is that we are asserting that there are exactly n events that exist in your data. But how do you know that there are exactly n events? What if there are some marginal events? Can you be sure that they were true detections or they are noise? You can't be sure, right? So is there a way to self-consistently incorporate these marginal events as well? So then you need to be able to come up with a rate method that is independent of the threshold, okay, and allows you to also incorporate marginal events. And that's what I will do after I complete the second thing, okay? Because I think that incorporating marginal events is slightly less priority than the second thing, because at least I want my lecture series to reflect what I've titled it, rates and populations. So I definitely want to talk a little bit about populations, okay? And then after that, I will go to how you derive the rate when you also have marginal events. All right, so let's go to populations. Is there a way to put this somewhere nearby? Yes, there is a way. All right, so now I'm going to try to answer the second question that I put down yesterday, or the second thing that I've put over there, which is suppose I have a collection of n events that I know are detections, okay? So I have so I have n events that are confident detections, and I assert that there are only these n confident detections, everything else is noise, all right? So then I do parameter estimation on each of these n events, okay? So once you do parameter estimation, you acquire the likelihood, So what you then get is a likelihood vector, and then you can convert that to a posterior vector. So what you get is p theta given x1, okay, p theta given x2, p theta given xn. So you have done parameter estimation on each of them, and you have sampled each of these possibilities using what we described yesterday. We defined the gravitational wave likelihood, right? And then from there we came up with the gravitational wave posterior. All right, great. Now the question that I want to ask is, what is the intrinsic distribution of the parameter in nature? So for example, I want to ask, what is the distribution of the masses of binary black holes in nature? Okay, are they preferentially lower mass? Are they preferentially larger mass? Where does this posterior peak, etc. Right? So I want to get that information, given that I now have all these posteriors on the individual events. Okay. So one way to do this, and this is perhaps the most popular way, at least in the LIGO-Virgo-Kagra collaboration, is you choose some ansatz, okay, on your population model. Okay. So essentially what you have to choose is some model. So what do I mean by this? Let's take one example. So one example of a population model is to say that, supposing I believe that my distribution of the heavier of the two components in the binary is a power law like this, m1 to the minus alpha. Okay? So this will be one example of what a hyperposterior is, or your population model is. It's a name that's used interchangeably, hyperposterior or population model. Okay? Does that make sense? All right. Okay, so then how do I construct my hyperposterior from my population model as well as the data? That's the question. Okay? So the posterior that I'm interested in is p lambda, given that I have the vector x. So given my collection of events, what is the posterior on the shape parameter? In this case, what is the posterior on alpha? Of course, your population model could be more complicated, involving other parameters, but in the most simple case, you want to determine what is the distribution on alpha. What is the posterior on alpha? Okay. So in order to do this, you start off as usual using Bayes theorem. Okay. So you say that this is px given lambda, p of lambda divided by your evidence normalization constant, right? So this is your prior. But because it is a prior on the shape parameter, this is typically also called a hyper prior. Okay? This is a prior on your shape parameter, right? And not surprisingly, this is called the hyper likelihood. And this would be your hyper evidence. All right. So the first step in order to evaluate this would be to determine what is your hyper likelihood. Okay. So what is px given lambda? Okay. Now here you can make a very reasonable assumption, and you can say that each of these events and detections that have happened in the data are independent of each other. So one event is not in any way correlated with the other event. Okay? Yes.
Very nice question.
Yes.
This prior, hyper prior, do you build on it as you detect events, or it is kept to some approximate model of the?
So usually it's actually kept mostly agnostic, except when there are some obvious reason where you know that the prior should not go there because it is mathematically not valid. But otherwise it's usually kept uniform. Essentially, if you find that your hyper prior is changing, your hyper posterior is changing as you change your hyper prior, that's a telltale sign that you don't have enough events in your data to make any meaningful statement about distribution of the parameter. Yeah. So for example, if you just had one event, it will be extremely sensitive to your, the hyper posterior will be very sensitive to your hyper prior. Because with one event, what distribution are you going to talk about, right? So as you increase the number, now we have come to a stage where it seems mostly independent of the hyper prior. The hyper posterior seems mostly independent of the hyper prior. Because now we have, for the first 3 observing runs, we had about 100 events, so that's already quite a bit. And I think with the end of the 4th observing run, we will end up getting probably close to 300 to 400 events. So then not only will this become largely independent of the prior, I think we will also get extremely strong constraints on this shape parameter. Okay. All right, so you want to construct the hyper likelihood, okay? And you are going to make the following assumption that your events are independent of each other. So then what you can say is that your hyper likelihood is just a product of the individual likelihoods. Okay? So this comes from assumption that So the next task is to determine what are the individual likelihoods on the shape parameters, right? So what is Pxi given lambda? Okay. So here you basically use the rules of probability and say that this is just Pxi given theta times P theta given lambda. Okay, and you have to integrate like this, right? Because Pxi given theta times P theta given lambda is just Pxi comma theta given lambda. So now you have a joint distribution, and then you marginalize out the nuisance variable. Okay? Yes.
So I think it's something not directly related, but
Yes.
regarding the assumption, what
Right.
do you do when you want to account for lensing where things cannot be, maybe they are not?
Right. So I think what is going to happen is that if you have events that are known to be lensed, they will be just removed from the data, because you will get to a stage where you have so many events, the majority of which are not lensed. You can say that you can remove the 1 in 1,000 event that is lensed, or the pair that is lensed from those 1,000 events, and it won't really affect your ability to constrain the shape parameters.
And that's the expectation.
Yes, yes.
Maybe 1 in 1,000.
Yeah, exactly, yeah. So I don't think we have too much to worry about that. What could become worrisome is in future detectors like LISA, where you have overlapping signals as well. And then you have to disentangle these signals very carefully. If you are unable to do that properly, then your shape parameter estimation will be completely biased.
But even in the case of 3G, right? I mean, we might
3G.
have overlapping.
Yeah. So there we have to really make sure that we disentangle. I see that as a big source of worry if we don't get a handle on it. Okay. All right. So any questions on this? Okay. So then, what is this? This is just your model, right? What I had put down as pi. So this is just this you can acquire from your posteriors, right? So you can write this as being so up to a normalization constant, this is true from Bayes' theorem, right? The posterior divided by your prior is just the likelihood up to a constant, right? So there. So yeah, everything here you know. You get the posterior from the parameter estimation, and you have assumed your model, the model that you want to fit, right? Okay. So then, you can construct your hyperposterior as simply the prior times the likelihood, which is a product of the individual likelihoods, and each of these individual likelihoods is just that. Okay, so this is then okay. Does that make sense? All right. So this is the hyper likelihood on the shape parameters that you need to sample from the individual likelihoods that you have for the individual events. Okay? But it turns out that this is not complete. Why is this not complete? The reason it's not complete is because of something that I mentioned yesterday known as the Malmquist bias. Okay? The Malmquist bias essentially tells you that the kind of events that you will see intrinsically depends on your detector's ability to see them. So your detector will intrinsically see sources that are brighter or with larger amplitudes, which means that your detector will see sources that are more nearby and larger in masses. Okay? So if you just did this, you will end up biasing your shape parameter, right? You will wrongly assume that intrinsically the universe is made up of more massive black holes instead of lighter ones. Okay? So you need to somehow account for this selection effect, the Malmquist bias. Okay? This, it turns out, is not trivial to derive, so I'm just going to put down the result here. You first need to construct what is called a detection probability as a function of your shape parameters, and this is So what this is telling you is that if supposing you know what is your detection probability as a function of the source parameters, then using your assumed model, you can get the detection probability as a function of the shape parameters, okay, in this way. Now the way you evaluate this is the same way that you evaluated for estimating the space-time volume sensitivity. You have to conduct a large-scale injection campaign where you inject your distributions of masses, spins, redshifts, etc., and then determine what fraction is recovered, okay? And that gives you your detection probability as a function of theta, your individual source parameters, okay? Now once you have this, you need to factor it in to your hyperposterior, and I'm just going to put down the result without proof. Okay. So this P det shows up at the bottom here, raised to the power n for each of the events. And I have rewritten what is inside the integrand in terms of things that you already know. So this you know from your parameter estimation of individual events. This is your model, and this is the prior. All of these things you know. So you should be able to calculate what is the hyperposterior on lambda, now accounting for selection effects, Malmquist bias as well. Okay. All right. So this was done, and I'm going to show some results. So I'll keep this side for the calculations. I'll just put down some notes related to what I'm going to show over here. Okay. All right. So what is this? These are the assumed models, mass models on the larger of the two masses, M1. Okay. So this is your pi theta given lambda. Okay. So there are 4 models that are assumed. One is called truncated, one is called broken power law, one is called power law plus peak, and the last one is multi-peak. Okay. Now each of these models are astrophysically motivated. Okay. So let us start with truncated. So if I say so the truncated power law is essentially motivated by something known as the Salpeter initial mass function. Okay. IMF for initial mass function. So what is the initial mass function? The initial mass function is essentially the distribution of stellar masses when stars are first formed. So this is something that was observed electromagnetically, and it was found to be nicely fit by a power law. Okay. So for distribution of masses when stars are first formed. So that's why you notice over here that this essentially has a power law feature, and the assumption is that this power law is between some maximum mass and some minimum mass, and there are no black holes below a certain minimum mass, and there are no black holes above a certain maximum mass. That is the assumption of this model. Okay. This model is known as the broken power law. So the broken power law has three features. It has one feature that is here, there's another feature that is here, and it has a smooth turn on as well. Okay. Let me actually just show the formulae, that might be easier. So let me start with, so this is your truncated power law. This is how it looks like. The truncated power law, like I said, is basically a power law in the primary mass, m1 to the minus alpha, and on the mass ratio, it is also a power law. Okay. This is, one second. This is the third model here. I have put down the third model, which is power law plus peak. So power law plus peak has also a physical motivation. So there is a power law portion here, which is your m1 to the minus alpha, and to that you are tacking on a Gaussian. Okay, so why is it that we do that? This is also physically motivated. You have a power law and you have a peak. So the power law comes from the Salpeter initial mass function. The Gaussian peak is motivated by something called pulsational pair instability. So what is pulsational pair instability? Okay. So what has been found from simulations is that stars that So stars with a mass that is greater than 150, actually, not 130. So stars with masses greater than 150 solar masses undergo a certain process where, because of interaction between So if you have interaction between gamma rays and nuclei inside these very massive stars, these interactions essentially produce electron-positron pairs. Okay? So you have E plus, E minus pairs that are produced. Now when you have these E plus, E minus pairs that are produced, essentially your gamma rays are getting converted to this via this interaction. Now if your gamma rays are getting converted, it means that the radiation pressure that is keeping the star propped up is now reducing. Okay? So if the radiation pressure reduces, this induces an initial collapse of the star. Okay? The gravitation tries to collapse the star, and this radiation pressure is not there to support it. Okay? Now, for stars greater than 150 solar masses, this initial drop or this initial contraction leads to a runaway process, a runaway thermonuclear reaction, and this eventually leads to a very, very massive supernova explosion that leaves no remnant behind. Okay? Does that make sense? Yes.
Can you remind me, this is way larger than the Eddington?
Yeah. Eddington
Eddington limit
for what? I mean,
for the. So where this number comes from? I mean, is it?
oh, this is found in simulations. Okay, so people have postulated that stars greater than 150 solar masses will basically create explosions, a supernova explosion known as a pulsational paired instability supernova that will leave no remnant behind. Now, so let me just write this. Pulsational pair instability supernova, okay? Now supposing you had stars between masses 100 solar mass to 150 solar masses, okay? So there again you will have this thing called the interaction between gamma rays and nuclei. This has caused the star to contract, but the contraction is not sufficient to trigger thermonuclear reactions, okay? So when the star contracts, again there will be production of gamma rays, and again the star will get expanded, okay, due to radiation pressure. Now when it expands due to radiation pressure, again you have interaction between gamma rays and nuclei, and this interaction between gamma rays and nuclei again produces E plus E minus pairs. So again there is a drop in outward pressure, so again the star contracts. So you have this back and forth pulsation that happens, okay? So stars between 100 and 150 solar masses undergo pulsational pair instability. It doesn't lead to a supernova, but this pulsation happens, okay? Now it turns out that during these pulsations there is a constant shedding of mass, okay? So when the star is pulsating, it is also shedding away mass, and as it is shedding away mass, it is becoming lighter and lighter and lighter until it eventually gets to 100 solar masses or less. And then when it gets to 100 solar masses or less, then you essentially have the usual stellar evolution that kicks in without this pulsational pair instability, and that results in an excess of masses at around 40 solar masses, okay? So notice one thing. Above 150 solar masses, you have no remnant. Between 100 and 150 solar masses, you have, due to pulsational pair instability, shedding of mass, which ultimately results in stars forming, in stars undergoing standard stellar evolution, and the remnant for these turns out to be at around 40 solar masses. So you now have an excess of remnants at around 40 solar masses, okay? So with this motivation, you put down this model called the power law plus peak, okay? So the power law plus peak essentially ensures that in addition to your usual power law, you are also accounting for the fact that you are expecting an excess at around 40 solar masses, okay? Now, because you have an excess at around 40 solar masses, and all stars above 150 solar masses are not leaving any remnant, after 40 solar masses, what you expect is a mass gap, okay? So this is known as the upper mass gap of stars or of black holes, where above about 40 solar masses, you don't really expect any binary black holes to be there, okay? However, in the last model, what is assumed is that you may still get some distribution of masses inside the mass gap, and the reason that can happen is because what is called hierarchical mergers, okay? So it may turn out that even though through normal stellar evolution, you may not get any masses that exist inside the mass gap, due to hierarchical mergers, meaning when black holes that are merging multiple times, and in that process their mass becomes bigger and bigger as they undergo multiple mergers, then you could have fairly massive black holes that lie inside the mass gap, okay? Does that make sense? Alright, so these are the four models.
So we can rule out power law plus peak, right? So we have now like even which is like 66 and 85 solar masses. So you just said like no
Right.
black holes can have greater than 40 solar mass for for the power law plus
Well, I mean, that's based on simulation. What your simulation is wrong? What if this whole pulsational pair instability thing is wrong? Right? I mean, one should not impose these things from beforehand and say that I know what is going to happen, right? So these are models, it's an ansatz. It's your assumption based on thinking that you know all the physics that happens inside a star. But what happens inside a star is extremely complicated, right?
but the answers should be tried out on the observational data, right? I mean,
Yes.
the data gives you a binary which is like the individual objects of
Right.
solar mass.
Correct.
So that is why like I'm saying like you can rule out the third.
Or it could be that the location of this 40 solar mass is wrong. Maybe the location is at 60 solar mass of this peak.
Okay, so the value does not matter, but the nature of the.
Yes, I mean, current simulation suggests that this excess should happen at 40. But what if the simulation got that part wrong and the excess should actually happen at 60 or at 70, right? So what is being done here is to come up with your best guess models of what you expect in nature, and you need to keep your models sufficiently flexible so that any missed physics is also captured, right? That's the idea. Okay, yeah, that's a good question. Any others? Questions?
Also, so what is the first peak actually?
Sorry, this one?
The first peak.
So this is essentially to ensure that you don't have a sharp cutoff here, right? Okay. So you don't want to say that suddenly at say 5 solar masses you start to have black holes. Suppose you want this to be a smooth turn on, and then after that you have a power law, and then you have another peak, and then you could have yet another peak as well due to hierarchical mergers. So these are all the models that are possible. Okay, or that have been assumed rather. Okay. Any other questions? All right. So let me see, where am I? So this is your power law plus peak, like I mentioned. So you have this power law portion over here. You have a Gaussian portion to account for the peak, and then you have this S function over here, which is your smoothing function to ensure that there is a smooth turn on. Okay. What you have here, this parameter, this lambda peak parameter, this is known as a mixing fraction. So you don't know how many of those black holes are coming from the power law portion of the distribution, and you don't know how many are coming from the excess portion, okay, the Gaussian excess. So you leave that as a free parameter as well, okay. So hyperparameter estimation was conducted, and this is a typical kind of corner plot that you get on the hyperparameter estimation. So you have here the power law portion of it, you have also the mixing fraction, and then you have the two shape parameters corresponding to the Gaussian, which is your mean and standard deviation, right? So this hyperparameter estimation was conducted, and they found a certain fit and values, okay? Now similarly, you had for the broken power law as well, you had a model, and then you have a corner plot that is made, and then for the multi-peak model, so this is the model where you have a power law, you have one Gaussian due to the excess and another Gaussian due to hierarchical mergers. So this, as you can see, has a power law portion, there is one Gaussian and there is yet another Gaussian, right? So that's why you have this multi-peak. And you have your two mixing fractions, the lambda and the lambda 1 as well, okay? And you have, of course, your smooth turn on. Yeah.
So I'm trying to understand the results or posterior distribution that we obtain from parameter estimation and population studies, right?
Yes.
In parameter estimation, we have the real data, we get bounds on suppose there is an injection, and we get 90% bounds, and we say if the bound, if the 90% is outside that thing, we say that the waveform model is missing something, right? But
Right.
in population studies, what we get as posteriors, we accept that as results.
But that is also the same for the individual events, right? You don't know a priori what the event parameters are, right? You didn't inject it in nature, nature injected it, right?
Yeah, but we are recovering it using some templates, right? I mean,
That's right, yes.
Yeah, so if our template is wrong, then we say.
Oh, your question is if your template is wrong, could it bias the hyperparameters? Yes, it will bias the hyperparameters, because if your individual parameters are biased, eventually a hyperparameter is not something that is intrinsically new, right? It is derived from your individual parameter, posteriors. So if this is biased, then definitely this will get biased.
So it's highly dependent on the parameter estimation result.
Yes, absolutely, yeah. Parameter estimation is kind of at the heart of this, right? You need to know what are the values of the individual source parameters. Then you can ask questions about what are the parameters on a population level, how are they distributed, etc. Right?
So on top of normal PE, for population study, you need the model on the population.
Correct. So PE also assumes a model only. That's your waveform model. You're assuming that the waveform model is correct.
But for population study, you need two models. One is the waveform and the other one.
Correct. Yes, correct. Yeah.
Can we do hyperparameter posterior by using posterior for individual events coming from different waveform models?
Typically, you end up doing that because it turns out that some waveform models are better at capturing certain portions of the parameter space than others. So for example, I think some waveforms might be better at capturing higher mass ratios. Some waveforms might be better at capturing comparable masses. So in principle, one uses multiple models. Moreover, when you want to do a hyperparameter estimation, say that also involves neutron stars, so then you need to have some waveforms that can also account for neutron star properties, such as tidal deformation. So if you now want to do a full mass model that incorporates both black holes and neutron stars, then one portion of the posteriors in your collection of posteriors will involve one type of waveform, and another set of posteriors will involve a different type of waveform. That has to be the case, right?
Yeah, but then how do you fold that difference between the models into this?
No, the assumption is that both are good representations of the signal in the data. So the assumption is that the waveform model that you have for neutron stars is a good representation for neutron stars, and the one for black holes is a good representation for black holes. That's the assumption. And all of this basically comes down to the fact that the only way we get a signal from the data is through matched filtering. And matched filtering needs a model to pull out the signal. It all comes down to that eventually. Okay. Yes?
Why the multi-peak model again comes down at the end, because now you can have any masses that can merge and.
Right. So the assumption here is that when you have hierarchical mergers, they typically happen in specific kinds of environments. So hierarchical mergers are more likely to happen in certain dense stellar environments where there is a chance for binary black holes to merge and become one black hole, and then again find another companion and again merge with that and do that multiple times. That can only happen in dense stellar environments. It cannot happen in the galactic field. Now in dense stellar environments, you know what are the typical distribution of masses or the expected distribution of masses of binary black holes over there. So then you can already make an assumption that, okay, see, if I know that in those dense stellar environments, the masses typically tend to peak at a certain value, then you basically ensure that you construct your Gaussian accordingly, okay? But again, let me just go back to this. So even though you know that in dense stellar environments you have a certain Gaussian distribution of masses, you are still leaving the shape parameters of the Gaussian as free. So you're not saying that my mean value has to be a certain thing and my variance has to be a certain thing. You leave that as a free parameter. The only assumption is that this is a Gaussian and it is not some other distribution. That's the assumption. Okay? And that comes from studies, and also I think Gaussian is always your first guess when it comes to distributions, right? So, okay, any other questions? Okay, so this was the multi-peak, and this is a portion of the corner plot of the multi-peak model, because if you put everything, it will not really fit here. So this is a portion of it. So you have your mixing fractions, and you have the Gaussian parameter of the Gaussian due to the excess at 40, the expected excess at 40 solar masses, and you have the second Gaussian's hyperparameters, which is due to the Gaussian of the hierarchical merger. So these are the posteriors that were derived, and as you can see, for the second Gaussian, the recovery is not that great. Okay, you can see that you are not very well constrained the variance of the second hierarchical merger Gaussian. That is not surprising, because it comes to what you had mentioned. We have so far seen only one event that is polluting the mass gap. So in the future, as we see more and more events polluting the mass gap, this posterior will also get more stringent. Our constraint will become better. Okay?
The priors on all these hyperparameters in these studies
Are uniform as far as I know, yeah. But I mean, you can double check these two papers, but from what I recall, they are uniform. Yeah. Okay. Any other questions? All right. If not, I will come to the last portion, and then we'll see how far we get on that. And that is, I want to come back to the topic of estimating rates, but this time I want to estimate the rate so that I don't in any way depend on the threshold. Okay? So a threshold independent way of estimating the rate of mergers. So let me put down some definitions first before I go to the full derivation. So this method that I'm going to use in order to come up with this rate posterior is a method that was developed by Farr, Gare, Mandel, and Cutler. So this is sometimes referred to as FGMC, named after the authors, right? So these are the people who developed this threshold independent method of estimating the rate. It turns out that they were actually not the first person to come up with the method intrinsically, but rather they were the first set of people to apply this method in the context of gravitational waves. This FGMC method is itself based on Lorido and Wasserman. Okay. And this was applied in the context of GRB detections. So this was a much earlier paper than FGMC. But nevertheless, at least in the LVK, this method is being referred to as FGMC. So I'm just going to call it FGMC. And what you will find is that this is once again simply an application of Poisson statistics. Okay? So, consider, as before, a data set where you have x1, x2, say you have xn events. Okay? And now here I am going to say that these x's are your ranking statistic values. So for example, they could be the SNRs. Okay? I now define a background distribution P naught x. This is a distribution. It's a probability density, which we talked about yesterday. Is a probability of getting a ranking statistic value x under the hypothesis of noise. P1x is the foreground distribution, which is the probability density of getting a value of x on your ranking statistic under the signal hypothesis. Okay? Does this make sense? Do you remember background distribution yesterday? We also talked about false alarm probability. Yeah? Okay. So this is your background and this is your foreground distribution. So now what I'm going to derive to you is that this likelihood on the Poisson means for noise and for signal so this is your likelihood. I'm just going to call it L of lambda 0, lambda 1 for short. So likelihood. This is proportional to exponential minus lambda 0 minus lambda 1 plus 1 to n lambda 0 p naught psi 1 p1 xi. Okay. So this is what I want to prove to you. Okay. So remember, this is your background and foreground distribution evaluated at the ranking statistic values of the individual events. Okay. All right. I now define a foreground probability, so not a probability density, but a foreground probability, capital P1, for an event with ranking statistic x, given that you know what the Poisson means are for foreground and background, or for noise and signal. This is lambda 1 p1 x, where lowercase p1 is your foreground distribution, so this is a density, divided by okay. So this is your foreground probability. Okay. All right. And the last definition that I want to put down is what is P astro. Okay? The P astro is simply this foreground probability marginalized with respect to your posterior on lambda 0 and lambda 1. So what we get from the data are posteriors on lambda 0 and lambda 1. We do not know exactly what they are. So your foreground probability can be used to calculate what is P astro, and this is going to be effectively a double integral on, okay? Does that make sense? So in order to be able to calculate what is P astro, you need to get your FGMC likelihood, from which you get the FGMC posterior, which is this. And from the FGMC posterior, you can get the rate, because that's what you require. When you calculate the rate, you need a posterior on lambda and you need Vt, right, the space-time volume sensitivity. And in order to calculate this P astro, you also need the FGMC posterior. Okay? All right. Great. So let us derive the FGMC posterior. So in order to derive the FGMC posterior, let me start as follows. Yes, I think I need this. Okay. Suppose your entire observation time t is divided into a large number of divided into a large number of intervals or sub-intervals. Okay. I just want to be a little careful in the notation. Okay. Oh, sorry. I'm going to say that is subdivided into n intervals. Okay. Now, let me suppose that there are m events. Okay. Now remember that here we don't care about the threshold, so these need not be confident detections. You just have a bunch of triggers in your data. There are m triggers in your data. Okay. So I can always subdivide my time interval such that n is so large that each interval contains either exactly one event or exactly 0 events. Do you agree with me? Okay. Does that make sense? Okay. So if I say that my observation time is capital T, then this subinterval delta t is just capital T divided by n. Okay. So you have several of these delta t's. Each delta t may or may not contain an event. Okay. Simple enough. Let me now say that since we have m events, there must be m intervals containing one event, and there are n minus m intervals containing 0 events. Okay. All right. So let me say that the intervals containing 0 events, I am going to denote them as a collection of phi j's, and the intervals containing exactly one event are obviously the events with their ranking statistic values, which I am going to denote as the vector x or xj. Right? So let me now say that here j goes from 1 to ... m because there are m events, and for convenience I am going to say that j here starts from m plus 1, m plus 2, ... n, because there's total of n subintervals, right? Does that make sense? Okay. Now, again I'm going to make an assumption. The assumption here will be that the individual events, gravitational wave events, are independent of each other. This would not be the case if you had overlapping signals. But supposing the signals are not overlapping, then assume that each of these gravitational wave events occur independently. Okay? So if they are independent, then what I can say is that my likelihood is proportional to this product okay, into I should probably put J. Let me put J here. J equals m plus 1 to n So let us study each of these separately. Okay. So what is this Pxj given lambda 0, lambda 1? Okay. This is the probability of getting exactly one event, because remember each interval contains only one event, right? Exactly one event with ranking statistic value between x and x plus dx. But since this is xj, I should say xj, right? So it's effectively a joint probability. It's the probability that you have exactly one event, and plus that event has to have a ranking statistic value between xj and xj plus dxj. Okay? All right. So now, let me write this down. dn by dt dx, this is the number of events or is the rate of events, so is the number per unit time, because there's a dt there, is the rate of events right? This is the rate of events that happens between x and x plus dx. Okay? So how do I calculate what this is? So first I can say that the number of events that happen between x and x plus dx must be equal to Do you agree with me on this? What this is basically saying is that the number of events between x and x plus dx is just the fraction of the total number of events for background that lies between x and x plus dx, and the fraction of the total number of foreground events that lie between x and x plus dx. Do you agree with me on this? Okay. So then, if I take a time derivative on this, effectively then I can divide this by the total time period, because each of these correspond to the average. So lambda naught by t corresponds to the average rate at which background events happen, and lambda 1 by t is the average rate at which foreground events happen. Okay. So this, for short, I'm going to say is just lambda naught dot p naught x plus lambda 1 dot p1 x. Okay. So dn by dt is just integral dn by dt dx into dx, and then it trivially follows that this is equal to, right? Because when you take this integral with respect to dx, you will end up taking these integrals with respect to dx, and since these are densities, probability densities, when you take the integral with respect to dx, they must go to 1, right? So what you will be left with is lambda naught dot and lambda 1 dot. Okay. All right. So we are going to use this when we try to decompose what is pxj given lambda naught lambda 1. Okay. All right. So what I am going to say is that when I try to decompose this, what I will get is pxj given So remember, this I had said is the probability of having exactly one event in interval j, and that one event has the ranking statistic value xj. So from the rules of conditional probability, this must be pxj given that there is only one event and you have your two Poisson means times the probability of getting exactly one event. Okay. So let us try to evaluate what is this now. The probability of getting an event with ranking statistic I given that only one event occurs. Okay? Yeah, it should be consistent with the notation. Okay? So this is just the number of events dn by dx dt evaluated at xj divided by do you agree with me on this? So this is the number of events per unit ranking statistic interval per unit time. Okay? If you divide that by the total rate, you will end up getting this conditional probability. Okay? The probability of getting xj given that you have only one event. Okay? So then this is simply lambda naught dot p naught x plus lambda 1 dot p1 x divided by lambda naught dot plus lambda 1 dot. Okay. Okay, now what about the other guy? This is actually very straightforward to evaluate. What is this going to be? Well, this probability of getting exactly one event, if we assume that events occurred as a Poisson process, this is just going to be lambda exponential minus lambda, right? Applying your Poisson distribution, where lambda I'm going to define as the total rate into the time interval delta t, because each interval has a time interval which is delta t. So the total rate at which the events happen times the interval delta t will give you what is the mean number of events that happen in that interval delta t, and given that you want this particular probability density, so P of 1 given lambda 0, lambda 1, you just use the rule or the distribution, the Poisson distribution. Okay? All right? So now 0 lambda 1 is equal to delta t exponential minus dn dt delta t. Okay. This now is equal to dn by dt times delta t is just lambda naught dot plus lambda 1 dot into delta t exponential minus lambda naught dot plus lambda 1 dot delta t. Right? Okay. Now, am I overshot or do I have like 5 minutes? What? Should I go on?
Yeah, please.
Okay, fine. Okay, so Pxi given lambda 0, lambda naught is a product of this fellow and that fellow, right? So this is, if you actually take this product, you will find that this lambda naught dot plus lambda 1 dot will cancel with this lambda naught dot plus lambda 1 dot. I'm going to let you guys do the algebra, it's very trivial. And what you'll end up getting is lambda naught dot p naught xj plus lambda 1 dot p1 xj into exponential minus lambda naught dot minus lambda 1 dot into delta t. Okay. All right. And I think have I done this correctly? And there is another delta t that will show up here as well. Okay. Fine. All right. So this is your Pxj given lambda 0 and lambda 1. Now, in your FGMC likelihood, there was another piece, right? That other piece was P of phi j given lambda 0, lambda 1. This is again trivial because if you assume that this happens as a Poisson process, you just apply the fact that there are exactly 0 events in those intervals. Okay? And what you'll end up getting is exponential minus dn by dt delta t. Okay? So now let me just remind you that your delta t is just the total observation time divided by the number of subintervals that you have. So therefore, lambda naught dot into delta t is simply lambda naught by n, and lambda 1 delta t is simply lambda 1 by n. Okay? So then, let me write down the FGMC likelihood. This is proportional to n delta t lambda naught dot p naught x j plus lambda 1 dot p1 xj into exponential minus lambda naught dot plus lambda 1 dot delta t into pi I j equals m plus 1 to n exponential minus lambda naught dot minus lambda 1 dot delta t. Okay, so this is now your full FGMC likelihood. Okay, now you can use the fact that lambda naught dot delta t is lambda naught over n, and lambda 1 dot into delta t is just lambda 1 over n. Okay, so using that and replacing here, you have delta t into lambda naught dot, delta t into lambda 1 dot. If you do all of that, what you'll end up getting is the following. Since I'm running over time, I will let you guys figure out the algebra, which again is not difficult. What you'll end up getting is that the likelihood on lambda naught lambda 1 is proportional to n raised to minus m exponential minus lambda naught minus lambda 1 pi j equals 1 to m naught p naught xi plus 1 p1 xi. Now this prefactor over here, n raised to minus m, is just a number. So eventually when you normalize your posterior, you really don't care whether this n minus m exists or not. So you can just leave it as a proportionality. And this is essentially your FGMC likelihood, right? And like I mentioned a bit earlier, from the FGMC posterior, you can define what is your astrophysical probability P astro, right? By using this FGMC posterior and marginalizing lambda naught lambda 1 out from the foreground probability. Okay? Alright, I think I will stop here. Yeah. At least I was able to cover rates and populations a little bit. I'd hope to cover some identities of this FGMC posterior and also talk a bit more about P astro, but it's fine. At least you have some idea of how rates and populations work in the LVK and with gravitational waves.